So we started looking at open systems where mass can come into and out of our control volume. And to do that, we need to know what happens to the mass. We know that mass cannot be created or destroyed. So we need to figure out what happens to it. Thanks again for joining me on Thermodynamics. Today, we're going to go through some examples for open systems for conservation of mass. So last class, we talked about how we've evolved from looking at closed systems to open systems, and how the first question we need to answer is what happens to the mass. We know that open systems are really practical systems that we see everywhere, like this car engine, which has an air intake and an exhaust out. We need to know where we draw the boundary for our system, in this case, so what is our control surface that goes around our system, and everything inside that control surface is our control volume. We need to know where to draw the control volume, and then now we're trying to figure out what happens to the mass, because we can't figure out what happens to the energy until we've accounted for mass coming into and out of our system. We talked about elapsed time versions of conservation of mass that say the change in mass in our system over time is equal to all the mass that comes in minus all the mass that goes out. We talked about a special case where we're at steady state, and at steady state, the mass in our system stays constant because everything stays constant. And that means that all the mass that comes in has to be equal to all the mass that goes out. Now, I also said in last class that usually when we're looking at open systems, we're not going to be looking at how a system changes in time. Instead, we're going to take a snapshot, an instantaneous view of our system, and figure out how things are changing in time. So we need a rate equation for conservation of mass, and that's what this is. Here, we have the rate of change of mass in our system. So is the mass increasing or decreasing with time? And to figure that out, we add up the mass flow rates into our system, and we subtract the mass flow rates out of our system. Again, we have a steady state version of this equation where dm by dt, or the change in mass with respect to time, is 0, which means that the sum of all the mass flow rates into our system has to equal the sum of all the mass flow rates out. So let's start to do some examples. So the first one, and maybe this is just because most of my life is spent watching Disney products, because I've got 3 girls under the age of 10 at home. And one of the shows that we've seen before is this idea of Mickey and the Beanstalk. What happens in Mickey and the Beanstalk is that Donald, Goofy, and Mickey, they're not doing so well, but they do have a cow. So Mickey takes the cow to the market, sells the cow, and comes back with some magic beans. Now, I don't know if you've seen this story, but Donald's not very happy about this transaction. So he takes the beans and he whips them out the window. But Mickey doesn't want to give up. So they have a 10-liter reservoir of water outside. Mickey knows that maybe he shouldn't have traded the cow for these seeds, but he wants to make sure that he gets something for this transaction. So he's got his seeds and he wants to water them. So he starts with 10 liters in the reservoir. On Monday, he waters the beans with 2.5 liters of water. On Tuesday, Goofy participates because Goofy kind of feels a little bit bad for Mickey, and he thinks that, we might as well grow some beans if that's all we've got left. On Wednesday, Donald, who's not that excited about the project, also waters the beans, but only 0.5 liter. Mickey sees the shortfall, and he adds 3 liters to the reservoir on Thursday and waters the beans with 2 liters of water. Goofy waters 1.5 liters on Friday. How much water is left in the reservoir on Saturday morning? So this is a conservation of mass problem, but it might not look like it, right? Because here we're talking about volumes of water every time we talk about liters. So embedded in this problem is the assumption that the density of the water, or the specific volume of the water, because we're in thermodynamics class, stays constant. So we're going to assume that the density is about 1,000 kilograms per meter cubed, or that the specific volume is 1/1,000 meters cubed per kilogram. We'll assume that we can neglect evaporation of water from the reservoir, so maybe they've covered up that reservoir. And now we think over time in the reservoir, how much mass do we have at the end? And in order to do that, we need to be able to think about all the mass that goes into the reservoir and all the mass that comes out of the reservoir. This one's pretty straightforward, and I'll let you do the calculations at home. But if you've seen the movie, you know what happens at the end. That they water the beans, and the beanstalk grows and grows and grows, and then Disney tells us that it's okay to steal from people that have more things than you do, right? They take this harp, they bring it back. Or at least that's what happens in the old version, right? And then in the new version, I think the giant comes down the beanstalk and they all become friends. So I guess we see that things are changing. But that's not usually how we're going to deal with conservation of mass problems in thermodynamics. Instead, we'll have a component like this turbine, and we're looking at it at a specific instant. Now, we're going to try to figure out all the properties or fix the states in position and not in time. So we're interested in how things are changing in space. So at the inlet to our turbine, we know we have a fluid, probably steam, at 10 bars, 500 degrees Celsius, and it has a volumetric flow rate. So I know this is a volumetric flow rate because it's area times velocity. I'm going to track my units, and I know that area is in meters squared, and in this case, velocity would have been in meters per minute. So I see that my volumetric flow rate is a volume, meters cubed, divided by some unit of time, in this case, minutes. Now at state 2, which is this outlet of the turbine, we know that the mass flow rate here is 20% of the total mass flow rate. We're also told that the pressure is 8 bar, that the temperature is 400 degrees Celsius, and we have a diameter for the pipe at state 2. At state 3, we know that the quality is 0.9, that the temperature is 90 degrees Celsius, and we're given a diameter here of 1.5 meters. We're asked to find V2 and V3, those are velocities, in meters per second. And we're going to do this by conserving mass in our system. We're also told that the problem here is at steady state. And if my problem is at steady state, that means that in my system, which will be the turbine, we're not storing or losing any mass. So the amount of mass that's inside the system stays constant in time. So I'm going to use the rate equation for conservation of mass here. So here I'm going to say that it's at steady state, which means that nothing is changing with time, which means that the mass in my system isn't changing with time. And that means that the sum of all the mass flow rates in is equal to the sum of all the mass flow rates out. So I know symbolically that all the mass flow rates in have to equal the sum of all the mass flow rates out. I only have one mass flow rate in, but I do have two mass flow rates out. So here, remembering that mass flow rate is the volumetric flow rate, or the area times the velocity, divided by the specific volume, and I can apply that equation at all three of my states, then my conservation of mass equation looks like this. I know my volumetric flow rate at state 1. I don't know my area at state 2. I don't know my area at state 3. I don't know my velocity at state 2. I don't know my velocity at state 3. I don't know my specific volume at any of my three states, 1, 2, or 3. So here I have an equation. I know one of the things in my equation, but there's a lot of things here that I don't know, so I'm going to have to spend some time to figure those things out. The first thing that I can do is I can remember that the area at a particular state or at a particular port on my turbine is going to be equal to pi d squared over 4, or pi r squared if you prefer, but we were given the diameters of these ports. So at state 1, I'm told the temperature and the pressure. I also know the temperature and the pressure at state 2, but at state 2, I'm told the outlet diameter, and I'm told that the mass flow rate at state 2 is 20% of the mass flow rate at state 1. At state 3, I'm given the temperature and the quality, So I know that's a two-phase mixture. And I'm also told the diameter at the outlet of state 2. Now, I'm not going to go through the table lookups with you here, but state 1 and state 2 are both superheated vapors. You can double check my work in your textbook if you like. But I found that the specific volume at state 1 was 0.354 meters cubed per kilogram, that the specific volume at state 2 was 0.384 meters cubed per kilogram, and that the specific volume at state 3 was 2.125 meters cubed per kilogram. I know from the diameter that the area at state 2 is 0.05 meters squared, and that the area at state 3 is 1.77 meters squared. So now I can put this information back into my equation. So I know my volumetric flow rate at state 1. I know now my area at state 2, my area at state 3. I still don't know my velocity at state 2 or 3. I know all of my specific volumes now. So we've done pretty well. We're now at a point where we have one equation with two unknowns. But I need another equation. And here, it's important that the problem has told me that the mass flow rate at state 2 is 20% of the mass flow rate at state 1. So I can make this substitution into the equation above and see that m dot 1 is equal to m dot 2 plus m dot 3, right? But since m dot 2 here is 20% of m dot 1, then I know that m dot 1 is equal to 0.2 m dot 1 plus m dot 3. And again, if conservation of mass applies and we're at steady state, I should see that if m dot 2 is 20% of m dot 1, then m dot 3 should be 80% of m dot 1, or that m dot 3 is equal to 0.8 times m dot 1. So now I know on my table that m dot 3 is equal to 0.8 m dot 1. So now let's try to figure out m dot 1. And if I know m dot 1, now I know m dot 2 and 3 as a function of m dot 1. So hopefully finding m dot 1 will let me solve the problem. I know this is the volumetric flow rate divided by the specific volume at state 1. So I was told the volumetric flow rate, and I found the specific volume. So I can work this out, and I get that this is 666.5 kilograms per minute. Now, it's not that kilograms per minute is incorrect, but sometimes I like to have my mass flow rates in kilograms per second. So we'll practice using a little bit of unit conversion here, and I'll get rid of the minutes by knowing that there's 1 minute for every 60 seconds. Here I put my minutes on top because I want to be able to cancel that out. I see that this becomes 11.1 kilograms per second. I know that m dot 2 is 0.2 times m dot 1, so that's 2.2 kilograms per second. I know that m dot 3 is 0.8 times m dot 1, and that's 8.9 kilograms per second. I could double check this by remembering that m dot 1 is equal to m dot 2 plus m dot 3, so 8.9 plus 2.2 does equal 11.1. So that's good. I can't prove that I'm wrong. So now I know m dot 1, m dot 2, and m dot 3, and I can put those into my table. But this is not what the problem asked me to find. The problem wanted me to find the velocities. So now if I look at m dot 2, I know that that's the area times the average velocity divided by the specific volume. I can rearrange this equation to get an expression for the velocity at state 2. And that will be the mass flow rate times my specific volume divided by my area. I know all of these values, so I can put them into my equation. As I go through the units, I see that this is correct, that I get an answer in meters per second. So I don't know numerically if my answer of 17.1 is correct, but at least I have the right units. My sign is also positive, so that's a good thing. I have velocity coming out where I'm expecting it to come out. I can do the same thing for m dot 3. Again, we'll use the same equation for the average velocity in the tube. Again, I'll take the values that I have in my table, and I find that my velocity at state 3 is 10.7 meters per second. So now I have answers for the thing that the problem asked me about. I have a velocity at state 2 and a velocity at state 3. So now that we're done, we got to ask ourselves, does our answer make any sense? So the first thing is that the units make sense, and that always feels good. So we can't prove that we got it wrong by looking at the units. So that's good. We got a velocity as meters per second, or distance over time, and that to me makes sense. Now it's a little trickier when we start to look at the magnitude of the two velocities, because here it's a little harder to get some intuitive sense of what's going on. We found in our problem that V2 was bigger than V3, but does that make any sense? We know that the mass flow through 2 is 4 times smaller than the mass flow through 3, right? Because at state 2, it was 20% of the mass, and at state 3, it was 80% of the mass flow. So that might lead us to believe that V2 would be smaller than V3, which is not what we found. We found also that the fluid is 5.5 times less dense through 3. So that might make us think that V2 would be less than V3 as well. But the area at state 3 is 36 times larger than the area at 2. So it's a little tricky to just look at the velocity here, because it's not volume that's conserved. It's mass that's conserved. So we need to think about changes in density and of the area that the fluid is moving through to find the velocity. And that's exactly what we did in this problem. So ultimately, we sort of have to trust our math unless we can run an experiment. And if you were designing something, that's actually what you would do. You'd start off maybe with an analytical model like this, sort of working a problem out with pen and paper. Then you'd maybe move to a numerical model where you'd relax some of your assumptions. And then you'd use that to sort of tailor your design. And then finally, you would make a prototype, which is the most expensive thing to do. But then you can see if the math that you're doing actually works in real life. So thanks for your time, and we'll see you again on the next thermodynamics lecture.